I'm Lukas Biewald. I'm the founder of a company called CrowdFlower, and I'm here to talk about my favorite topics, which is transfer learning and active learning and all of the theory about machine learning that you really need to do to make your models really work in the real world. And maybe like level of technical background in machine learning. The talks look super technical, but a lot of times I feel like I give these talks to audiences and they're a little less technical than I'm expecting. So that might be helpful too. My goal with this talk is to really just to kind of give you a high level overview of all the exciting things that I think are happening. And then I'm going to point you to a whole bunch of papers to kind of go further if you guys want to go deeper. So hopefully that will satisfy every level of technical interest. So today, we're going to talk about my favorite topics, like I was saying, training data, active learning, transfer learning, and a little bit about synthetic data. I think these are actually the most important topics that I see if you want to really deploy machine learning models or deep learning models for real world applications typically. I want to start off by talking about a couple graphs why I started my company CrowdFlower. When I was in school, we spent almost all of our time focused on improving algorithms. And I have some little toy data in the lower left where I built a topic classifier, and I used naive Bayes, maximum entropy, and SVMs, which is a little more advanced. And trying different algorithms, you go from 19% accuracy in this case to 17% accuracy. And you can see there's millions of papers, like I have in the right-hand side here, where you try something and then you try something more advanced and you get a 5 or 10% improvement. And that can be really exciting for publishing papers, and it's really important. But in the real world, sometimes you need much bigger improvements. And one of the ways you can get those improvements is the effect of better features. Or with deep learning, I think it's even kind of beyond features, not just the sort of traditional vectorizing your data we used to talk about, but how do you frame your data? How do you transform your data before you put it into the algorithm? So I'd include things like building, slightly modifying your data with vision algorithms so that it gets lots of different, you're translating your data and shrinking and growing your data. And this is, I think, what people these days spend a lot of their time on if they're at big companies trying to get an algorithm launched. And I tried this on my data set, feeding in unigrams, bigrams, and then unigrams plus bigrams. And you do get much bigger, typically much bigger feature or accuracy improvements when you feed in better features, right? Here we go from a 27% error rate to 16% error rate, and that's fairly typical, right? So that could be the difference between launching an algorithm and not launching an algorithm. But what they don't tell you in school is that almost all of the features that you try, they end up not really mattering, right? So you publish your paper, or you try 100 things, then there's only 1 or 2 things that actually really end up improving things. So there is one thing that I really believe almost always improves your models, and that is adding training data. And this is so simple to say, but so hard to do in the real world. But I just want to show you the effect of this on the data set that I had. And here I went from, and I think N was around 10,000. It was a fairly small hand-labeled data set that I had with a 13% error rate. And then going up to 4N, I got my error rate down to 5%, right? So this was a massive improvement, bigger than any of the feature engineering I could do, or way bigger than any of the model building or algorithm improvements. And I think it's kind of funny on the right, this is from a paper I found about using different machine learning techniques. And the point the paper is trying to make is that green line is a little bit better than the red line in terms of accuracy. But the real dominant effect here is the x-axis in this graph on the right is actually the amount of training data they fed in. So you could basically erase all the impact of the paper just by doubling your training data set. And so if you have a chance to do that, that's almost always the better thing to do. Then there's one more effect that nobody talks about, but everybody knows in the real world, and this is the effect of actually taking your data, which almost always has errors in it or unexpected values, and finding where those errors are and removing them or reclassifying them can be incredibly powerful. And actually can't find a paper that really does this, but I did it on my synthetic or my hand labeled data set. And what I found was that going from 90% accurate to 95 halved the error rate, and then going from 95% accurate training data to 100% accurate training data actually halved the error rate again, which is pretty massive important performance increase. So this is not a deep theoretical insight, but it's something that we always forget to do. If you're working on a problem right now and you want it to get better, look at your data and clean up your data. And hopefully you got your money's worth just from that tidbit of advice. We always forget to do it. So let's talk a little bit about training data. You know, one of the things that inspired me to start my company was Peter Norvig's essay, The Unreasonable Effectiveness of Data. So this was about 10 years ago. He wrote about basically the cases where machine learning worked really well was when they happened to have really gigantic data sets that were naturally available. And this was said more precisely maybe by Banco and Brill, who are at Microsoft Research, and they showed this graph here that you've probably seen a million times where x-axis is the number of words in the training set, and then y-axis is the algorithm. So all these different algorithms they tried on this use case, basically the accuracy steadily improved as they added words to the training set. And so, you know, my company CrowdFlower, and this is not meant to be an advertisement, but I love my company. I founded it. I need to tell you about it a little bit. We basically have a tool where you can get more training data. And this could be actually as complicated as labeling every pixel in an image with, is it sky, is it road? Or it could be as simple as just building a yes, no, what level of support is this support ticket coming in? We handle all different kinds of machine learning use cases, and we help our customers collect training data. And I really believe that what I'm doing with CrowdFlower is super important, because if you look at where you see breakthroughs in AI, it's almost always soon after a data set is made available. So this guy, Alexander Wissner-Gross, actually published this table, which you might quibble with the specific examples that you see here, but the dominant effect is that the algorithms that we use for these big breakthroughs, like all the advances that we see in object classification, they happened pretty quickly after Imagenet was collected. So Imagenet was a corpus we'll talk about where it's, you know, over 1 million labeled images that had never been seen before, but convolutional neural nets had been around for quite a long time. Cool, so I see a question, what worked better, a 4N, but 90% accurate data, or an N, but 100% accurate data? And you know, I would say I always kind of urge people, if you can, to go for the more accurate data set. I think smaller and accurate is almost always better. It obviously matters, you know, N and the use case and exactly what the trade-off is. But I think when I look at across watching thousands of people collect training data sets, almost always a smaller, cleaner training set is better. But when these huge data sets are made available, you see big breakthroughs in AI. And so I think it's actually interesting to go back to that Banco and Brill graph, right, of kind of what happened, right? Because that was 10 years ago. And, you know, 1 billion words in a training set actually feels kind of small now, right? I mean, that's certainly not web scale. So we can actually look at what happened at 10 billion words, 100 billion words, 1 trillion words, you know, kind of what happened. And really what happened was deep learning happened, right? So really, and this is according to Andrew Ng, one of the real leaders in deep learning, the thing that pushed deep learning forward was actually the fact that older learning algorithms couldn't really exploit the amount of data that we're starting to see. But deep learning, we can make them deeper and deeper as we get more and more data. And actually Google published this awesome research paper 10 years later, and they have an excellent blog post, but I recommend reading the paper. So this is the unreasonable effectiveness of data revisited, right? So, you know, Peter Norvig was talking about millions of examples, but they wondered, you know, what happens if you get 30 million, 100 million images for object detection? And what happens is that the models just keep improving, right? So, you know, at every scale of training data that we see, the models just steadily improve and improve and improve. So to the extent that you can get training data, that's going to be really fantastic for you. But you know, training data is expensive, and so if I could give machine learning practitioners kind of one area of research to look into that I think will really help, that really could make the difference between deploying a model and never getting to deploy a model. It's active learning. And this has been an active area of research for 20, 30 years, but I think it's becoming especially important now. And so the general framing of active learning, right, is you have a model and you have a whole bunch of unlabeled things, right? So this might be, you have, there's almost an infinite amount of images, but how many of them are labeled with what's in the image, or how many faces are labeled with the bounding box around the face, or how many websites are labeled with the topic or the relevance of the website, right? So whatever it is, typically you'll have a lot of unlabeled sets of data, right? So and there is a whole field of machine learning called there's a whole field of machine learning that kind of handles dealing with unlabeled data, right, called unsupervised methods. But typically the things that really work in the real world are around supervised methods. And so you have an oracle, right? So this could be a human annotator, or it could be some expensive process. I know in the medical field, this can be really expensive. But basically you want to take your unlabeled data and get the labels that you need. But if you have a choice on which things to get labeled, you can actually do smarter than picking from your unlabeled pool at random. And so the first thing that you should do, the simplest thing that actually really, really helps, which is much better than picking at random, is you pick the examples where your classifier is not confident, right? So this is actually super useful because the examples where your classifier is not confident, if you actually want to deploy something, having a human label those, you actually can get high quality output, right? So in real world systems, we often see this design pattern called human in the loop, where, for example, the post office, when they get a letter they can't read, they send it over to a human to try to read it when their OCR system breaks. But actually, a byproduct of that is that the things that you're labeling where your classifier is struggling, you are doing active learning. You're actually picking the best examples to improve your classifier over time. And there's a lot of theory on this, but you kind of illustrate this with a little toy problem here, right? So if you look at figure A in this, imagine you're trying to classify the green squares versus the red triangles, and imagine you basically can turn over green squares and red triangles, but it's expensive. So B is the line you get if you overturn, I think, 30 of these things at random, right? And it's actually not a very good classifier, right? It's like on an angle. But if you iteratively overturn and look at if something's a red triangle or a green square based on the things where the classifier has uncertainty, right? These are things close to your line. You actually get a much better line, right? So the difference between B and C here is not subtle, right? In fact, the accuracy, it's 70% accuracy versus 90% accuracy, right? So this is a huge difference with the same amount of training data collection. And so there's lots and lots of papers on this, but sampling, they call it uncertainty sampling here, is much better than random. And so actually this graph shows as you add more and more queries to your data set, or bigger and bigger training data, how your accuracy changes. And if you actually look at any particular horizontal line in this graph, you'll see that in this case, actually doing uncertainty sampling means that you get the same accuracy as about collecting double the number of random samples, right? So another way of looking at it is you generate your training data set at half the cost with the same level of performance in a model. So this is really something that you really should do in almost every case. There are now some situations where uncertainty sampling can be bad, right? And that's where uncertainty sampling kind of pulls in things that are kind of irrelevant to your model. So I think this figure is from a paper that sort of shows, right, like overturning A here, right, where the model has a lot of uncertainty, but it's a really unusual sample. It's kind of outside of the region of things that we care about, might not be as good as overturning B here, right, which is actually kind of closer to the things that we care about. So there are some ways. I mean, I think if you just do uncertainty sampling without anything else, it's kind of the very best thing, the very best first step you can do, and too many people don't do it. But if you want to get even fancier, you can try to handle this case, right, where you're actually looking at not just where you have uncertainty, but where it's in the region of things that you're likely to care about. And in medicine, you get this a lot where you want to label regions that you think are kind of interesting, right? You might have a wide swath of regions that are kind of like all uninteresting points of data, and you want to kind of do a first pass where you look for things where it might be, for example, a cancerous cell, or the kind of, if you have a very unbalanced distribution, you might want to do a first pass that sort of looks for the less frequent thing in your data, right? So you generally want your labels to be more balanced rather than less. So other applications where it can get really interesting and complicated, and I actually worked on this personally in search at the beginning of my career, is, if you want to sample web pages, right? So if your question is this a relevant search result or not a relevant search result, if you actually take random query and random web page, it's almost always irrelevant, right? So you almost always want to do a first pass where you're looking for relevant examples and then getting those labeled. But you actually can have regions of your data where there's still a lot of weird things happening, right? Any region that you haven't sampled things from can create problems. So one of the things that we found when we were trying to deploy ranking algorithms is that you had to run your model in production and see what the model brought up, what the model was pulling into the top 10, and then get those labeled, and then build a new model. And then you'd run it again. It would kind of dredge up strange things from the internet. And you had to do that 5 or 6 times before the model started pulling up weird results, right? So, most of the things out there are not relevant to any particular query, but you need to find the regions where your model is confused in order to make a model that you can actually deploy into production. So these are all kind of different forms of active learning where you're trying to pull in data sets that are important or interesting for you to label, because in medicine it can be really expensive. In the web search application, there's just so many websites out there for any particular query that you really have no chance of getting a representative sample of all the websites you might find. So in the different fields, the active learning can have different meanings or different strategies, but almost always you want to pick things where your classifier has a lot of uncertainty. And so you can see this is a good paper on active learning where it sort of shows a couple different techniques, and the overall conclusion is basically that doing any kind of active learning at all is much better than doing no active learning. So I strongly recommend looking into that. And there's another related field that's actually becoming super, super popular, which is, or super interesting, which is transfer learning. So everybody's been talking about transfer learning lately, I think especially because deep learning lends itself so well to it. But it's been around for quite a long time, right? So people have been thinking about transfer learning, and there's so many different situations. I think this is a great flow chart of kind of which different types of transfer learning you're doing. But the sort of most canonical cases where you have labeled data in one domain, and it's kind of similar to another domain, but you don't have as much labeled data in that domain. So I'll run you through a couple of examples here. I mean, one case is if you want to classify 2 sets of news groups, and then you want to classify a different news group, right? So this is, you can tell the age of this paper, right, by rec versus talk versus size. So these are actually, this is a classic data set of different news groups, and the idea is to go from the text to classifying which news group you're having. And so it basically, if you take 2 topics, right, so say it's like a DVD news group versus a book news group, and then you want to classify electronics versus book, you can actually use some of the power of the model that you've built on the first pair and apply it to the second pair. And that almost always helps. And this was even before deep learning. But deep learning makes this extra powerful, especially because there have been some humongous data sets released, right? So there's an awesome audio data set, an incredibly large-scale data set of audio events. There's Imagenet. Actually, my company, CrowdFlower, has a whole bunch of data sets on our Data for Everyone site. So there's giant data sets out there, but sometimes it's unlikely that the data set exactly fits what you want to do, right? For example, Imagenet has a ton of images around plants and animals, right? It just happens to be, the taxonomy came from a thing called WordNet that was really deep in kind of plants and animals, and maybe less deep in some other things we might care about, like packaged goods. And even when the data sets line up, I want to show you, see there's some robots that I built in my basement. And these guys are trying to classify things like that guitar and that hammer. So one of the issues that came up is actually these cameras are wide angle cameras, right? So guitar is actually in Imagenet. Actually, this is a ukulele, I guess. But acoustic guitar is pretty reasonable. But these robots actually kind of struggled because the kind of images that you collect online actually look pretty different, right? These robots are low to the floor, and they have a wide angle camera. And actually, this is kind of subtle but really important. Images online in Imagenet, a human being kind of framed them. So the topic of the image tends to be in the middle, whereas robots don't frame images, right? Because they're just looking around. So one of the things I had to do to get those robots to work was actually do some transfer learning to, even though it was exactly the same taxonomy, it was just a subtle different type of images that adding just a little bit of images straight from the robot data really improved things. And a more practical use case, so this is a data set where actually some of the CrowdFlower customers will care about this. So this is basically taking images of candy and pasta and other foods, right? So this is something that is really lacking in Imagenet for whatever reason. This is a groceries data set. So a totally different set of classes. So you might think, man, if I want to build a groceries classifier, do I have to start all over? Do I have to, in order to get the same performance that we see in papers, am I going to have to collect, a 2 million record image data set? And luckily, it turns out you don't, right? So this may be, remedial for you guys who are kind of already deep into deep learning, but these deep learning models, they have a lot of depth, right? So this is different than some other models, right? And one of the really cool things about a model like Inception is that it has all these layers, and we can actually see that these layers are kind of doing different things, right? So this is an early layer, and there's actually a really excellent blog post I'm pointing to. If this is new to you, you should definitely go and read it. But if you go into an early layer, what you'll see is that the filters are really recognizing just very simple kinds of textures. And as you go kind of further close to the output layers in the neural net, you can see that the layers are recognizing more and more complicated things. So the intuition here is that these layers could actually, at least the layers that are sort of closer to the input, could actually be useful across different data sets. So it could be that food and the images from Imagenet could have a lot of overlap in terms of classifiers. So the first thing you can do is you can use the neural nets as feature extractors. So you can actually take the output of Imagenet and you can build a classifier on literally output, because Imagenet is about 1,000 classes, so our neural net's going to output about 1,000 numbers. And if you build a new classifier on top of that, you can actually sometimes build a very good classifier for example, these groceries. So that's a simple thing that you can do where you don't have to modify the neural net in any way. You just basically run the neural net, take the 1,000 numbers that it outputs, and use them as a new feature vector. This is really simple, and a lot of people do it, and it's incredibly powerful, especially when you have really small data sets that you want to classify on. There's another thing you can do, which is called fine-tuning, where you actually take out the last layer. So the last layer is the predictions of the categories, and you replace it with a new layer that makes new predictions, and then you retrain it. So you leave all the weights that you had trained on typically on ImageNet if you're in the image domain, and you let it retrain itself. And this is super cool for two reasons. So again, I'm pointing you to a blog post that another blog post you should definitely check out on GitHub. But on this groceries data set, you actually get much better performance when you take the weights that you had already. In fact, the loss difference doesn't even show this, but you go from 47% accuracy on that small grocery data set to 77% accuracy. And who knows? I mean, that could get even better with more fine tuning. there's actually an incredible paper in Nature recently where they did this with skin cancer. So they had about 100,000 skin lesion images, which are, I assume, very, very hard to collect. And that's still kind of a fairly small data set. And I think medicine often has trouble getting really big data sets at the same scale. Oh, please share the blog links in the chat. Okay, cool. I'll try to do that. If someone else could type them in, that would be really helpful. But yeah, so I really recommend checking out this paper because actually the fine tuning here worked at a scale that or I guess in a different domain that is a little bit surprising. I mean, this feels a little magical to me that we were able to train something on pictures of dogs and trees, and it helped with skin lesions detection. And the effect was not subtle. I mean, this was actually better on specificity and sensitivity than real dermatologists. I was really impressed with this. And actually, someone wrote this excellent paper, Best Practices for Fine-Tuning Visual Classifiers to New Domains, which I think if you want kind of a primer on all the different fine-tuning trade-offs you can make, they really do a good survey of the literature. And I would say, just to summarize it for you, the best thing you could do is basically you take the last layer, you remove it of your neural net, and you replace it, like I was saying, with a layer that has the output that you want. You freeze some number of the initial layers, and then you typically want to use a much smaller learning rate than you would if you were training something from scratch. And they have some data with different data sets where they have different number of categories and also different levels of distance. So here, cosine distance, they basically mean they're trying to measure like how different the different data sets are from each other. And they try fine tuning versus freezing, where the freezing is like you just take the output of the neural net and then you classify off of it. And basically what they found was that when you have a really small number of new data and your new data is really close to your original large data set, you should typically use freezing. And when your data is really different, or when you have lots of examples of the new images, then you should definitely do fine tuning. So kind of a continuum here. Actually, both of these are pretty easy to try. There's lots of online tutorials that will help you get started doing fine tuning and freezing. But anytime, especially with images, just because these image classifiers are so good and the Imagenet is such a rich data set, you should almost always be doing fine tuning and or freezing, at least trying it. A lot of people ask me, which model should I start with? A lot of people are concerned about that because there's more and more models out there today. And it used to really matter, right? So these are results from a paper where they talk about, is it better to use LinNet, AlexNet, or VGG? So this paper is maybe 2 or 3 years old. And they find that basically VGG is almost always the best model to start with. And VGG is a big model. Actually, some people have made models like SqueezeNet where they tried to make them smaller and faster to run. And I think one of the cool things is that sometimes these smaller models can actually work better for fine tuning. So not only do you get a performance benefit, but you get an accuracy benefit at the same time. And there's even a pretty exciting new paper that came out where basically people are trying to learn architectures, not just to do the image classification initially, but to build an architecture where it's transferable. So literally trying to build an architecture where the transfer learning will work well. And so here you have NASNet, which is the thing that they built. And what they find is that actually it works better than all the other models that they tried. But I think here you're starting to see the benefits are a little more subtle, right? So it's kind of going from 80% accuracy with ResNet to 82% accuracy, things like that. And so I think the overall effect is basically any of these models like ResNet, Inception, or you could try NASNet, they all work really well for this transfer learning at this point. And I kind of wanted to show you, if you haven't seen it before, the different the different other ways that you could take a model and transfer it to a pretty different domain. So bounding boxes feels pretty different, right? You could frame this as regression as opposed to a classification, but you can still take these ImageNet trained models and use them in cool ways. So not to go deeply into it, but basically you can take, one strategy is you can take the image regions and then run them through your trained, ImageNet trained convolutional neural network. I think one awesome example of how this works And I'll email out all these links. I realize it's probably too quick for you guys to, you probably can't cut and paste this, but I'll put them all in the chat at the end of this. But these guys are, if you say you wanted to do an image classification here, right, you can actually look at what the neural net is doing, and you can see that one of the convolutional layers is actually really lighting up right at the two places where those guys' heads were. So we can make an intuition that we can take our pre-trained models, and they're actually going to give us a lot of information in terms of doing things like face recognition and bounding boxes. And semantic segmentation is pretty similar, right? So if there's a classic paper on convolutional networks for semantic segmentation, they do the exact same thing, right? Where you have the same setup, and you're pulling out of I think in this case they used VGG, but they're basically pulling out not just at the very end, but they're pulling out the activations of the neurons at multiple layers at the same time, which actually gives them, because the models tend to pull and shrink the layers in each step, you're actually pulling out information from different scales at different times. So you don't necessarily even just want to reach into one layer to pull out information, but you can do it from multiple layers at once. And the results are super, super cool. And so again, just kind of giving you a survey that's, I think there's in natural language processing, you have word embeddings, which is pretty similar, right? Where you have a model that's trained on a massive data set, and you apply it to a whole bunch of things at once. And there's bilingual word embeddings, where people try to do word embeddings in multiple languages at the same time, which I think is an incredibly promising and interesting area of research, since the intuition is that meanings are kind of broadly across languages. And there's a great paper, How Transferable Are Neural Networks in NLP Applications, which again is a good survey of the different things that you might try. And basically what they find is that these neural nets actually, again, work super well, where depending on how similar your data sets are, you might want to kind of lock down more parameters of the network. And if you actually look at the unreasonable effectiveness of data revisited, you can see that they're actually doing, they're comparing doing fine-tuning versus not fine-tuning. So here they got a new data set, but the question is, do they start with Imagenet and add these examples to it, or do they train it from scratch? And again, starting with Imagenet really helps. And so again, just trying to give you a survey. There's a related topic that you guys should be aware of, which is multitask learning. And this is where you want to learn multiple things at the same time, right? So you might want to recognize faces. You might also want to put waypoints around people's faces. You might want to see, what their emotion is. And you can imagine you might want to share some parameters from all these different models. So, one reason to do this is just performance, right? You don't want to run a separate nose classifier, an eye classifier, and face classifier. But actually, there's a reason to it beyond performance, which is that the accuracy improves when you put all these things into a single model. And I'll just say there's sort of, there's a trade-off here. You could do what's called hard parameter sharing, where you have a lot of shared layers and then you branch out at the end. Or you could do what's called soft parameter sharing, where you basically constrain, you train a bunch of different models at the same time, but you constrain the layers to be somewhat similar to each other. And there's different ways to do that, but a Google search will find this. And if you're doing multiple learning at the same time, this is something you really should consider looking into. And then finally, there's an active area of research now, one-shot learning or zero-shot learning or few-shot learning. So this is like, how do you build a classifier when you literally have no training data? And I think one just really cool insight, right, is that, say you built a classifier, you wanted to classify a spatula, and you've never seen a spatula before, right? Humans can kind of do this, right? Provided you frame the problem, not just like, I'm showing you new things and name what they are, but I'm showing you pairs of things and saying, are they the same two things? So instead of building an object classifier where it says, what is this, right? Because that's brittle to an object that it's never seen before. You train a classifier where it says, here's two objects, maybe taking the photo from different angles, or two versions of the same object, and are these the same thing? And this is called a Pairwise or Siamese network, and this works. This is kind of the only chance you have to do this kind of zero-shot or one-shot learning, and it's an exciting area of research for really, really small training data sets. But you can think of it as a type of, an extreme type of transfer learning. The last thing I wanted to cover is synthetic data generation, which I think is a really exciting direction that we see a lot of CrowdFlower customers taking, and maybe you could put CrowdFlower to business, or a way that you can generate humongous training data sets. And I think this started with people using things like Grand Theft Auto or some of these awesome video game engines to do semantic segmentation. Because if you think about it, if you generate these semantic segmentations in a video game, you already know where the cars are, you know where the trees are, because the video game had to have that information in order to generate these images. So what's super cool is that you can generate an infinite amount of data very quickly by using these synthetic approaches. The concern is that the data might be different than your actual model. But one of the things that I did actually was I trained a classifier on these bottles, and these bottles actually look pretty bizarre. I painted totally unrealistic textures, and then from that I built a robot that was able to pick up screwdrivers. So the images don't actually always have to line up with exactly the images in the real world, but there are a ton of weird effects that can happen, as you might imagine, when your training data is different than your real world data. But you could think of it maybe as a transfer learning problem, right? Where you want to transfer from the synthetic world where you have an infinite amount of data to the real world where you don't. And I think general adversarial networks, which is a hot topic, has a role to play in this, right? Where you try to build a discriminator that classifies between real world samples and generated samples. And I don't think people have really figured out how to make useful training data out of this, or I haven't seen a lot of work, but the data that these generative adversarial networks produce certainly looks in a lot of ways plausible, and like it could be fed into vision algorithms or others. So I think this is kind of greenfield research topics right now, but I think people are spending so much time on it because training data still is so incredibly important for making neural networks actually work in the real world. So I think my time is up. If you guys want to learn more, I wanted to give you guys a way that you could kind of reach out and contact me. I'm working on a whole bunch of different projects right now. So if you go to bit.ly/learn-more-ml, I can reach out. I can email you some links from this class. And if you have any questions or feedback, I thought I wasn't sure how well this chat thing would work, but I'd love to learn more about who's actually watching this and what you took away from it. And yeah, I'd love it if you're interested more in training data. CrowdFlower has a great blog where we've put a lot of stuff, and if you want to see more of these weird robot projects that I'm working on, check out LukasBiewald.com. So I think my time is up there. But if anyone wants to put any questions in the chat, happy to talk about it. Oh, these are interesting questions. I mean, these are kind of deep questions. So, I'll say transfer learning and NLP. I think a lot of the research in transfer learning actually started in NLP, and so if you look at a lot of the older papers on transfer learning, they're using all language applications. I was kind of looking for more papers that kind of more modern. Deep learning and NLP transfer learning papers, and I wanted to point you guys to a good one, but I wasn't sure what was the best. I think the sort of most important example of transfer learning in NLP is probably here. I'll go to a video if I can here. Sorry, my computer's freaking out a little bit. But yeah, word embeddings I think I really do think word embeddings is kind of the most powerful example of transfer learning. And then, meta learning is interesting. I mean, I think it is actually a special case of transfer learning. I mean, I think of it more as sort of like, I think of kind of like it's hyperparameter sharing, but I guess you can, in a way you could think of hyperparameter sharing as a type of transfer learning, kind of like a loose, like sharing a hyperparameter is a pretty loose way to take data from, learnings from one domain to another domain. Yeah, and okay, so semi-supervised also, I mean, again, all this language, I think we don't totally have precise language. So I think I would even say transfer learning is a type of semi-supervised learning. That's why I had that flow chart in the beginning of my slides on kind of like, what you call these different situations. Yeah, if you guys fill out my little survey and say hi, I'll send you I'll send you all the slides so you'll have all the links. And if you guys disagree with anything I'm saying, by the way, you know, let me know. I'm not sure I have all the language perfect across all these different fields. And yeah, you know, I haven't seen research on using GANs on other than Imagenet. I'm positive people are working on it. It's just Imagenet is kind of the most fun, right? To show off what you're doing. So I've seen it on images and videos, but I'm 100% sure a Google search would find something on text. In fact, I'm tempted to kind of, you know, look for it myself. Anyway, I think probably a good stopping point. Thanks so much, guys. I really appreciate your time. Yeah, let's keep in touch. You know, shoot me a tweet or fill out my survey, or yeah, have a wonderful afternoon. Take care.